Hello and welcome to the fourth of the lectures in this week 7 of this course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In this lecture, we will see how to build a Mamdani fuzzy inference system to approximate a given function. Towards this end, we will take the help of the Fuzzy Logic Toolbox that is available with Matlab. A quick recap of the salient points that we should remember when we want to build a fuzzy inference system. We know that a fuzzy inference system approximates a given system function by covering it with overlapping rule patches. We have also seen that matching functions from the given matching functions like Zades and that of Smith-Magri, we came up with a generalization of a matching function, and it is this matching function that is implemented in the Fuzzy Logic Toolbox that is available with Matlab. So we will look at using this for the current lecture. We've also seen that for this class of matching functions, in the presence of singleton fuzzification, that the similarity value of an input essentially becomes the membership value of that input x0 to the fuzzy set represented by the corresponding antecedent. We have seen in the last lecture a quick intro, general intro to build what it means to build a Mamdani fuzzy inference system using Matlab. What are the components that we need to look into? In this lecture, we will actually build a Mamdani fuzzy inference system using the Fuzzy Logic Toolbox in Matlab, and we will look at each of the components and how to source them, how to find them, how to fine-tune them. All of these things we will see by taking two simple functions and trying to build a Mamdani FIS to approximate it. A quick reminder about the terminology. So we know that a similarity-based reasoning consists of these many parameters of degrees of freedom. Px is the fuzzy covering on x, Py the fuzzy covering on y. R of AI Bj, it represents the rule base that we have considered, where AI, the antecedents are coming from Px, and Bj's, the consequents are coming from Py. H is the fuzzifier, M is the matching function, J is the modification function, G is the aggregation of the output, so it's an aggregation function, and small g is essentially the defuzzifier for us. This is the family of matching functions that we will be looking into in this lecture. So essentially, to specify or fix a matching function would mean to essentially fix these two operations, which are typically fuzzy logic connectives, and at least the outer operation needs to be associative. In Matlab, the fuzzification is singleton fuzzification by default, and the matching function is called the AND method and OR method. So the combination of these two will give rise to the matching function. These are the corresponding inside and outside operations. Modification function is called the implication. Aggregation and defuzzification are known by the same terms. Now, what is important for us to realize is there are these many degrees of freedom. Let's for the moment go with the default fuzzification that is available for us, the singleton one, which means rest of these 7 degrees of freedom will have to be fixed. Now, even though it appears like 7, we have to be very careful here, because in matching function we again have 2 degrees of freedom. These are the parameters or degrees of freedom highlighted in blue are perhaps easily fixed in Matlab, and it's easy to fine-tune them. Whereas these which are highlighted in red, we need to be extremely careful. Of course, we can fine-tune them also, but we need to be very careful and choose intelligently these parameters. What are they? Px, the fuzzy covering on x, the fuzzy covering on y, and once we have picked up these coverings, how to relate a fuzzy set from Px to a fuzzy set in Py to relate them as rules. We will see this for 2 different functions. The first function that we'll consider is, as was mentioned earlier too, is the identity function, which is a simple linear function. Now, let's look at building a Mamdani fuzzy inference system for this identity function. So we have the domain here. X is from 0 to 1, y is from 0 to 1. So essentially the graph of this function is going to be within this square. This is the graph of this function, the identity function, which is essentially the diagonal on this square. The first question is, how do we choose Px and Py, the fuzzy coverings? Now, typically we need to position these fuzzy sets on the domain X, and what we do is pick a few points in the domain of X. Let's say that we pick arbitrarily these 11 points, equispaced points from the 0, 1 interval, which is our domain X. And next, we can build a fuzzy set around this. So we have seen that we could build a triangular fuzzy set at each one of these points. So essentially taking this as the center and defining what should be the length on the left and right side. Now, similarly, we also need to look at finding points on the domain Y, which is our range here. Towards this end, since we know the function here, all we need to do is for each of these xi's that we have chosen, let us look at what are the corresponding f of xi. So now if you take 0, it is 0. If you take 0.1, it is 0.1. 0.2, it is 0.2, and so on, because it's essentially the identity function. So now that we have this, let's assume that we are going to take these points as the prototypical points and we are going to build fuzzy sets around them in such a way they actually form a cover of the domain and the range, the domain of Y and domain of X. Now it is clear that if we actually draw triangular fuzzy sets with each of these points as the middle, center, and extending almost to both of the neighboring points to the left and the right, then it is clear that they will form a cover. In fact, if you take the triangular fuzzy sets, they will in fact form a Ruspini partition. Now, what next? Once we have this, how do we relate the fuzzy sets on X to fuzzy sets on Y to build a rule base? Now, this is where the idea of patching the system function with rule patches comes into picture. So now, one way to do it is, let's look at how to actually cover this function with rule patches. So perhaps one way to do it is like this. You will see that this rule patch essentially starts at this point. Maybe if you call this x0 and x1, starts at x1 and perhaps goes little more than x2. And similarly here, starts at y1 and goes little more than y2. And this is how the rule patches are. So it is clearly indicative that we are perhaps looking at supports of these fuzzy sets to actually cover these intervals on both the x and y axis. We will use this idea to build the fuzzy system. So essentially, we are just covering this function using these patches, and this gives us an idea as to how we need to form the fuzzy covering on y and also on x. So if you type in fuzzy, the term fuzzy in Matlab, what you would get is this window. A few things can be seen here. So these are the parts which specify the different operation that we are going to use. So as was mentioned, this AND method and OR method together, they specify the matching function that we are going to use. If it is min and max, then essentially it is the ZS matching function. Implication refers to the modification function. You can use a minimum operator, which is min here, already as given as default. And for the aggregation, there is this max. And for defuzzification, the default option is centroid. So essentially, with singleton fuzzification as the default, and once we fix all these things, so these two fix M, this fixes J, this fixes the aggregation G, and this fixes the defuzzifier small g. Now what we are left to do with are these three important things, Px, Py, and the rule base itself, R of AI, Bj. So let's start with that. So now we need to define what the input membership functions are. Let's name this as X, and let's name this as Y. So it's a mapping from, or maybe f of x. It's a mapping from f to f of x. Perhaps y is better. So now, if you double click on this, you will see that Matlab, the Fuzzy Logic Toolbox, loads 3 triangular membership functions by default, and it takes the domain also to be 0. That's the default thing. And as it happens, happily, this is the domain that we need also. Now the question is, how are we going to build a cover for this domain 01? We have got some inkling. We have seen how to do this from the previous figure that we generated, that to take 11 points, 0, 0.1, 0.2, so on till 1, 11 equispaced points on both the domain and on the codomain, and then build fuzzy sets around that. Let's build triangular fuzzy sets around this. That means if you look at it, is called MF1. Right now the names do not matter to us because they are just only approximating a pure mathematical function. So let's assume MF1 refers to the first membership function. So to remain consistent, what we'll do is we'll position this MF1 around the point 0.1. So now you see here it's a trapezoidal membership function, which means it takes 3 values. So we want to position it around 0.1, and we allow it to extend till the previous point 0 and the next point, which is 0.2. So you see here immediately it adjusts. Then for MF2, what we'll do is we'll do the same. We will position it from centering it at 0.2 and allow its support to be from 0.1 to 0.3. Now we can do this for every one of these. Allow me to quickly finish that. 0.2, 0.3, 0.4. So now we have these 3 fuzzy sets on this. Clearly they do not form a cover. So we need more fuzzy sets. What do? Go to this edit menu, add membership function. Let's add triangular membership functions. We have 3, we need another 8 more. And you will see that they are everywhere. Of course, they are arbitrarily drawn. So let's look at MF4. And by our convention, what we want is we want to position it at 0.4, which means, so this is MF7. So it makes it easy for us in terms of the labeling. So it's centered at 0.7. It's MF8. So it will be centered at 0.8. So the support of it will be from 0.7 to 0.9. So we have a MF10, which means it will be positioned at 1. Now, if you want to have a triangular membership function centered at 1, which is essentially the end point, then we will be extending outside of the range that we have considered. So we will saturate it at that, and we'll keep it as 0.91. So this is how it will look like. This is MF11. We'll come to this in a moment. MF9. So it should be centered at 0.9, which means the support of it is okay. This is MF6. So its support will be from 0.5 to 0.7. Once we take MF5, so support is, we have done this, but we have not defined what it is for 0. So let's call this MF0, and once again we want to place it at 0. The right endpoint of the support is 0.1. Since we cannot go below 0, let's saturate it at 0. So this is how we have actually made the fuzzy covering on the domain X, which is 0, 1 interval. You will see that for every point there is some fuzzy set to which it belongs to a non-zero membership value. In fact, it can be easily seen these are linear functions. So it is also clear that they actually form a Ruspini partition. So this is the fuzzy covering that we have come up with on the domain. Let's do the same also for the output. So this is 1, so which means by our convention we'll do this. 0.1, 0.2, 0.3, 0.2, 0.3, 0.4. So now we have 3. We need to add further membership functions. Once again, we'll add 8 of them and proceed with the same thing. So we'll start from here. It's easy. 8 it is. So that means it should be positioned at 8, 0.7, 0.8, 0.9. 9 is 0.8, 0.9, 1. We have seen that it has to be positioned at 1, and so it saturates at 1. This 11 we will rename it as 0. It's clear again, it cannot go below 0, so it will be positioned at 0, but to be like this. MF7 will be centered at 0.7. Its support will be from 0.6 to 0.8. For 6, it will be centered at 0.6, but its support will be from 0.5 to 0.7. Now, what we are left with is MF4. Okay. So this will be centered at 0.5, and finally we have here MF4, which will be centered at 0.4. Well, so we now have all the membership functions that we need. That means we have come up with a fuzzy covering on X and fuzzy covering on Y. In this case, both of them are just the 0, 1 intervals. Now the question is, now we have this Px and Py. How do we frame the rules? Note that we have seen that it's an identity function. So essentially what we have in mind is whatever value we give, A dash, that should actually come out as B dash. So the commonsensical way to build the rule base is to match the corresponding fuzzy sets from X and Y, or from Px and Py. How do we add rules? So now Fuzzy Logic Toolbox helps us here. Now on this side you have all the rules, all the input fuzzy sets listed. This side all the output fuzzy sets listed. Now you see here MF1. So what we want is the fuzzy set centered at 0.1 should also be related to fuzzy set centered at 0.1. So highlight both of these and say add a rule. Next, highlight these two and add a rule. So essentially for the identity function, all we need to do is this. Makes it easy. And of course, we will also see a next function, which is not simple or straightforward, but still not very complex. So I'm relating 0.7, the fuzzy set at around 0.7 to fuzzy set around 0.7, fuzzy set around 0.8 to fuzzy set around 0.8, fuzzy set around 0.9 to fuzzy set around 0.9, and fuzzy set around 1 to 1, and also finally fuzzy set around 0 to 0. Well, so these are the 11 rules that we have. How do they look like? There's a very nice visualization. Now, so this is your input domain, this is your output domain, and these are the fuzzy sets that we have, and these are the rules. So this is A1 implies B1, A2 implies B2, so on and so forth. Now, already we have chosen these operations. So we are set. We have found the fuzzy covering on X, fuzzy covering on Y, and we have also related them and found the rule base. So now, when we come here, this is one quick way to give an input and find out what the corresponding output is. When X is equal to 0.5, we get 0.5. Now, if X is equal to 0.3, you see here, Y is also equal to 0.3. So this is exactly what we wanted. We wanted to approximate the identity function. Now, if you look a little deeper inside this, what are we doing here? Now, this is at 0.5. You can look at this straight line, this red line, as actually the singleton fuzzification. So now what happens is at point 3, it takes the value 1 in this fuzzy set and nowhere else, because we have a Rushmani partition here with triangle membership function. And so the similarity value is 1, and we are look at the modification. The modification is minimum. So we are taking this 1 and we are thresholding this membership, the consequent membership function here, which is, if you call them B1, B2, B3, we are thresholding this B3. However, since it is 1, essentially everything comes through. And what are we using here? We are using the centroid defuzzification mechanism. Okay. So next thing that we need to understand is, okay, for 0.3 and 0.5 it happens. What about other values? Will it happen? Yes, we can try for a few of these. You see there at x is equal to 1.13, y is 0.133. So there is some discrepancy here, but it is approximating. That's because when we have this, you see here there are 2 of these getting highlighted. So the similarity value here is taken and it is being thresholded here. Similarity value here is being taken and this is thresholded here, and we are using maximum for the aggregation and centroid defuzzification. Let's see whether by changing these, whether we can obtain some better values. So towards that end, I hope you are able to see. Let's, instead of using min as the modification function, let us try to use the product. And you will immediately see, while the similarity values have not changed, what has changed is the way it is being thresholded. So now it is being essentially scaled. And once again, after scaling, we are still using the maximum aggregation function and the centroid defuzzification. And you see that, in fact, it turns out that the value goes down. Instead of having 0.133, we are going towards 0.127. It is still not the identity function, but it has actually fallen down. Now we can play around here. Instead of max, if we take essentially the sum of membership functions, you see here with this aggregation, we are actually coming up with exact value. What is referred to as sum here is essentially the Lukasiewicz-Tikhonov. So when you use the Lukasiewicz-Tikhonov, which is min of 1, x plus y, we see that for 0.13, we essentially get exactly the same identity value. So by tweaking these different degrees of freedom, by choosing these functions intelligently, we can actually approximate a given function. In fact, it has been proven in theory that any continuous function can be approximated using there exists a Mamdani fuzzy inference system with a particular choice of operations which will approximate the given function that is under consideration. Okay, so now here we have given a few values and then we have seen what happens to it. So 0.89, 0.89. But how long can we go on? Because 0 to 1 there are infinitely many numbers. Is there a way to see whether this is the function that it is approximating? What has it understood? Well, there is a way to see it. Now if you look at this, the graph of this function, the defuzzified values, for each of the values that you give here, for x, you get a y, and you see here this essentially your identity function. Thus, what we get here is essentially the function that we wanted to approximate, which is the identity function. And along the way, we have seen a few things, that every degree of freedom that we have can make a difference. While operations are easy to choose, but once you choose them, you see that the overall output is going to change. And what we have to do is intelligently pick the fuzzy coverings on x and y and intelligently relate the rules if you want to approximate the given function under consideration. Now, let us look at the second function that we will be approximating. Well, the first function we saw was that of a simple identity function over the 0-1 interval. Let's look at a different function now. It is from -1, 1 to the 0-1 interval, essentially the x square function. While the identity function is both linear and monotonic, we see that x square is a nonlinear function and also not monotonic. Between -1 and 0, it is decreasing, and 0 and 1, it is increasing. However, let's apply the same logic that we applied to build a Mamdani fuzzy inference system to approximate this function. What do we have now? This is the domain of x -1 to 1, and this is the domain of y, which is 0, 1. And the function we are considering is the x square function. Once again, we need to pick points on x and y so that we can build a fuzzy covering around those points. Once again, let's pick equi-spaced points between -1 and 1. So there will be 21 of them. And as we followed earlier, let's find the corresponding f of xi's to find where to position the fuzzy sets so that we can come up with a fuzzy covering on y. So at -1 it is 1, at -0.9 it is 0.81, and if you go like this, these are the corresponding f of xi values for each of the xi. And this gives us an idea clearly that perhaps we should be looking at these points as the prototypical points around which we could construct the fuzzy sets to form a fuzzy cover. So now, it is clear that once we form the fuzzy sets around these points, then we need to intelligently relate them so as to form rules. It is clear that if you are taking -0.8, then we should relate it to 0.64, and similarly if you are taking 0.7, we have to relate it to 0.49. It's the same thing with when x is, if we are considering the fuzzy set which is centered around -0.7, because it's x square, we would look at relating it to the fuzzy set which is centered around 0.49. Now, let's go back to our idea of patching up this function with rule patches. How would they look like if you took the supports on either side to be a constant? That means on x we have constant support fuzzy sets, and similarly having constant support fuzzy sets on y also. So as was explained, this is how we should map the fuzzy sets on x to fuzzy sets on y. These are the rule patches that we would get if we fix the support, the width of the supports, assuming that we are considering triangular fuzzy sets. The width of the support is to be equal on the corresponding domain. We see here that while it is actually nicely patching up, overlapping with overlapping patches, here we see that the patches are not overlapping, and hence these values are lost. The function is not approximated there. It clearly shows two things. Firstly, that it is not always possible to have nice we may get symmetric fuzzy sets, but often we need to compromise on many things to be able to approximate the function. Of course, the overall goal is to approximate the function. And if you are using equi-width support fuzzy sets on y, it is not going to cut the deal for us. That's the first thing. Secondly, you see here the support of this fuzzy set centered around 0.81 is only from this point to this point, and you see that if you consider such fuzzy sets, they will not form a fuzzy covering on y. We have seen this, that we have insisted only on a fuzzy covering on x to call it a complete rule base. However, to be able to approximate the function smoothly and completely, we would need often a fuzzy covering on y also. We will make use of this approach again in constructing a Mamdani fuzzy inference system to approximate this function x squared. Well, I have taken the liberty to populate the input fuzzy sets the way we have discussed it. So here are these 21 fuzzy sets, as you can see, equispaced. Clearly, they form a cover. They also form a Ruspini partition. Similarly, on the output domain between 0 and 1, we have only 11 of them because It's an x square function, an even function. So we have only 11 such fuzzy sets. We need to relate these 21 input fuzzy sets to these 11 output fuzzy sets. Now, at this point of time, let us also recall what we had mentioned or seen earlier, that largely when we have a rule base, we have more input fuzzy sets than output fuzzy sets. This is typical, and we have seen here now that there are 21 such input fuzzy sets and there are only 11 output fuzzy sets. Now, how do we relate them? Once again, it is clear that we relate them as follows. That we relate, if 1 relates to 0.1, then we are relating it to the square of 0.1, and if 11 relates to minus 0.1, we are again relating it to the corresponding membership function 1 of 0.1. So this is how we have done this. If you would like to see the rules, it's perhaps much easier to see there. You will see here that 0 is mapped to 0, 1 is mapped to, or 0.1 is mapped to 0.01, 0.2 is mapped to 0.04, and you could see almost it is tapering in the way x squared tapers. And you should also notice that these are not constant with fuzzy sets. And you will see from here that for every input that you have here, we don't give the input on y, but you would see that any element that you take from y, every element of y will find some bi here, to which it will belong to a membership value greater than 0. There are far too many things for us to notice here, but let's give the value 0, and what we want is 0 square, and you see here it is 0.167. Let's give the value 0.5 and see. You see here it is 0.257. So it's approximating it quite well. If it is 0.9, you will see it is 0.817. Well, this is what happens. Now, let's do one thing like in the earlier case. Let's try to change some of the operations and see what is it that we get. For 0.9 here, we have got 0.817. Let's change this product to minimum. Now, that will not make any difference because we are talking about singleton inference. So all it will come out when we are using a different t-norm or any t-norm at all for that matter, when you are using the z matching function, is the membership value of this input point x0 to the corresponding antecedent. Instead, what we'll do is we'll change the modification function and see whether it has any effect. In this case, it doesn't seem to. At 0.5 again we get this. Now instead of aggregating using sum, let's do it with max. But of course, we have taken a point which is non-overlap on two things. Yes. Now you see here, when it is 0.4, it is 0.016. When it is 0.45, you get 0.22 when we are actually using maximum aggregation. I'm going to change it here. It's very easy. So if you use sum, you see that automatically it goes to 0.218. Instead of centroid, if you use some other defuzzification, since it is not clear in this diagram here, we will change it. We will not change it now. We will look into defuzzification, the different defuzzification methods, how they change. Perhaps when we take up building a TSK fuzzy system to approximate a function. Well, so this in a nutshell is how you build a fuzzy inference system, a Mamdani fuzzy inference system to approximate a given function. Of course, the immediate question is, in this case, we knew the function that we need to approximate. There was no need to approximate this function. However, as was mentioned earlier too, we are only learning the tricks of that trade, given it is only some kind of a proof of evidence that any function can actually be, any continuous function can actually be approximated using Mamdani fuzzy inference system, and also a way of doing it, how to actually pick the fuzzy covering, how to pick the rules, and what are the operations or options that you choose for the different inference operations. In general, we do not know what is the function that we are going to approximate. The system function is not known, but we will have some data which is coming from the system, and using that data we build the inference system. We will see an example of it in one of these lectures this week. A quick recap of what we have seen so far in these lectures. We know that a fuzzy inference system approximates any given function through overlapping rule patches. In this particular lecture, we have looked at how to build a Mamdani fuzzy inference system to approximate a given function. Of course, the function is known and we were trying to approximate it. So essentially, we took the information from the given function itself. However, in practical applications, it is not often that we know the exact system function. However, we will know some information about the function itself, some qualitative information about the function, the system function, perhaps about its monotonicity or about its oscillatory properties, or some qualitative properties about how it behaves over different subdomains, or perhaps essentially that the graph of the function is band limited between some region. Making use of this, we may be able to build a fuzzy inference system, and often we do using these heuristics. We will see in the next lecture one particular case where we will take a practical application and show how to build a Mamdani fuzzy inference system for that. For this, we will take the case of enhancing the contrast in a given grayscale image, and we will see how we obtain the qualitative nature of the system function that we are trying to approximate, and using that, how we build a Mamdani fuzzy inference system. This is what we will take up in the very next lecture itself. Glad you could join us for this lecture, and hope to see you in the next lecture too. Thank you again.